Aldol condensation is a fundamental reaction in organic chemistry used to create carbon-carbon bonds. It involves the reaction of an aldehyde or ketone with another carbonyl compound to form a beta-hydroxyaldehyde, often followed by dehydration to form an unsaturated product. The key to this reaction lies in the acidity of the alpha hydrogens. Because of the electron-withdrawing nature of the adjacent carbonyl group, these hydrogens can be removed by a base, turning the carbon into a nucleophile. In the first step, a base-like hydroxide removes an alpha proton. This creates an enolate ion. This intermediate is stabilized by resonance, spreading the negative charge between the alpha carbon and the oxygen atom. The enolate now acts as a nucleophile. It attacks the electrophilic carbonyl carbon of a second aldehyde molecule. This step is the heart of the reaction, where the two smaller molecules link to form a larger chain. After the attack, we are left with an alkoxide intermediate. This negatively charged oxygen is highly reactive and will quickly look for a proton to reach a more stable, neutral state. The alkoxide ion abstracts a proton from water or the solvent. This regenerates the hydroxide catalyst and yields the aldol, a molecule containing both an aldehyde and an alcohol functional group. If heat is applied, the reaction often continues. A molecule of water is eliminated through a dehydration process. This usually occurs via an E1CB mechanism in basic conditions, leading to a more stable conjugated system. The final product is an alpha-beta unsaturated carbonyl compound. The double bond is conjugated with a carbonyl group, providing extra stability through resonance across the 4-atom pi system. Let's look at an example using propanol. Note that the bond always forms at the alpha carbon. In this case, the branching at the alpha position results in 2-methyl-3-hydroxypentanol before dehydration occurs. In a mixed or crossed aldol reaction, we use two different carbonyls. If one molecule, like benzaldehyde, lacks alpha hydrogens, it cannot form an enolate, which helps control the reaction to produce a single major product. Because the enolate is planar, the nucleophilic attack can happen from either side of the carbonyl group. This typically results in a racemic mixture of enantiomers unless a chiral catalyst is used. While we focused on the base-catalyzed mechanism using enolates, aldol reactions can also be acid-catalyzed. In acidic conditions, the reaction proceeds through an enol intermediate instead of an enolate ion. It is important to remember that the aldol reaction is an equilibrium. Under certain conditions, the retroaldol reaction can occur, breaking the beta-hydroxycarbonyl back down into its original components. Aldol reactions can also happen within the same molecule. If a molecule has two carbonyl groups, it can undergo intramolecular condensation to form stable 5- or 6-membered rings, a common strategy in total synthesis. To summarize, first, base creates an enolate. Second, the enolate attacks another carbonyl. Third, the oxygen is protonated. Finally, heat drives the loss of water to create a double bond. Test your knowledge: which carbon atom acts as the nucleophile in this reaction? If you chose the alpha carbon, you are correct. It is the site where the enolate's negative charge is concentrated. The Aldol condensation is a pillar of synthetic chemistry, used to build everything from complex pharmaceutical drugs to industrial polymers. Mastering this mechanism is essential for any organic chemist. You now understand the movement of electrons that drives the Aldol condensation. Keep practicing these mechanisms to master organic synthesis. This lesson was generated by Vision Solve AI.